So let's talk about Ampere's law. Ampere's law was discovered, well, the effect behind Ampere's law was discovered around 1819, actually by a physics lecturer who was in the middle of a lecture, and he noticed that a magnetic field was generated that moved around a compass needle when he ran a big current through a wire. So the law basically says that currents, if I run a current, it will generate a magnetic field. Now, there's multiple ways of stating this law. There's the Biot-Savart law. There's Ørsted's law. The standard way to present it is in terms of Ampere's law, which basically says that whenever you've got a current, you'll have a magnetic field that circulates around that current. Now, in order to determine the sense of that circulation, what you do is you use your right hand and you grab the wire with your thumb pointing in the direction of the current. When you do that, your fingers will show you the sense in which the magnetic field circulates around. So if you got the current going that way, the magnetic field is going to make little circles around the current in this sense. So in the front, it'll be going down. In the back, it'll be going up. Beneath the wire, it goes into the board. And above the wire, it goes out of the board. So that's the idea. Now, what Ampere's law also says is that the magnetic field circulation, and by that we basically mean the magnetic field times the length of that circulation, is proportional to how much current we've got. So if we double the amount of current, then we're going to double the size of the magnetic field. All right, this also gives us a very, very, very easy way to determine a closed form expression for the magnetic field due to a long wire. So here I got a wire with a current coming out of the board. So that's why you don't see the wire, because the current's coming out of the board. Now, the magnetic field is the blue line. Notice that, again, I grab the wire with my thumb pointing in the direction of the current, and my fingers indicate how the magnetic field circulates. Now, Ampere's law says that the magnetic field circulation, which is the magnetic field times the length of this curve, which is 2 pi r because it's a circle, is proportional to, that means it equals a constant times the current that's coming out of the board. Now, what is this constant? Well, we could actually measure it, but in reality, what people do is they use the freedom that we have to define the ampere as a unit of measurement in order to make this constant exactly 4 pi times 10 to the minus 7 in SI units. So those units are Tesla meters per amp. All right? So 4 pi times 10 to the minus 7. That's mu zero. It's called the permeability of free space. All right, so when I've got this expression, I'm going to solve for B, and it gives me B equals mu naught I over 2 pi r. So that means if you double the distance that you are from a wire, you're going to have the magnetic field. If you triple the distance from the wire, you cut it in thirds. All right, let's do an example with this result. So I want to know what the magnetic field is 2 centimeters away from a wire that carries 5 amps of current. All right, well, I can just do this directly. B equals mu naught I over 2 pi r. So I'll just plug in 4 pi times 10 to the minus 7 times 5 amps divided by 2 pi times, all right, what do we know we need to do? We need to change it to SI units, or else our magnetic field will not come out in Tesla. So 2 times 10 to the minus 2. All right. Now at this point, wonderful things happen. Look at this. 4 pi, 4 pi. Bye-bye. All right. So now we end up with 5 times 10 to the negative 7 plus 2 is negative 5 Tesla. All right. Or 50 micro Tesla. All right. So that's the magnetic field. It's not a really big magnetic field, and 5 amps is a fairly large current. So when we do this just with a long straight wire, generally we don't end up with a huge magnetic field. We'll have other ways to do that later. All right, suppose that I want to determine the force between two long wires. So here's the idea. Got two long wires, they're both carrying current. This long wire, I used the right-hand rule, and that means that there is a magnetic field into the board here at the second wire. All right? But now, a wire that carries current in a magnetic field, it feels a force. What is that force? Well, IL cross B. So that force is actually attractive in this case. It's going to pull the wire up towards it. Well, how big is that force? Well, geez. The magnetic field, a distance d away from wire with current I1 is mu naught I1 over 2 pi d. Okay? The force is the second current times the length of wire times the magnetic field, which I can rearrange like that. Now, usually what people do is they'll divide by the length and they'll get a force per unit length that's given by this formula. Notice that we got mu naught, we get the product of the two currents, and then we divide by 2 pi d. Now, this is actually how the ampere is defined. The amp is the current that gives exactly a force per unit length of 2 times 10 to the minus 7 newtons per meter when you have two wires carrying the same current and they're 1 meter apart. So that means that this is 1, this is 1, this is 1, and I need the whole thing to be 2 times 10 to the minus 7. So that means mu naught is 4 pi times 10 to the minus 7. And that's where the definition of the ampere comes from, and that's Ampere's law.